Anton Burkov. He is my classmate from the university. So we did together master degree in the same group in St. Petersburg, and then he went to the US to do his PhD with Solomon McDonald, and I went to Sweden. So then after that he was a postdoc at Harvard, and first KTP, USB with Leon Balance, and then at Harvard, and now he is a professor at the University of Law.
Okay. First of all, I would like to thank the organizers, in particular Igor, for inviting me to this beautiful workshop. I'm having a lot of fun, and it's also my first time in Stockholm. It's a really nice city. I'm really impressed. So I'll talk today about incompressible vortex liquids and water isolators in 2 dimensions. I mean, you may legitimately wonder what the vortex liquids and water isolators have to do with each other. Hopefully, it will become a little bit clearer at the end of my talk. So in case you're interested in details, most of what I'll talk about is published in this reference. So this is the outline of my talk. First, I'll start by introducing the system in which the physics I'll talk about is realized. So the system is interacting bosons in 2 dimensions in perpendicular magnetic field. Okay. So then I'll discuss sort of the basic schematic phase diagram of 2D bosons in magnetic field as a function of the filling factor. Okay, so in particular I'll discuss the 2 sort of groups of phases that occur, the repulsive vortex lattice of large filling factors and the incompressible vortex liquids of low filling factors. And so then finally I'll talk about my own work, and so the main point of this work is that fractional quantum Hall liquid of bosons can be mapped onto a Mott insulator on triangular lattice. Okay, so you will see how this happens. Okay, so 2D bosons in perpendicular magnetic field. This is the system, the physical system that I'll be concerned with. So there are many experimental realizations of this system. So maybe the oldest one is thin film amorphous superconductors in perpendicular field, where a superfluid to insulator phase transition is observed as a function of the strength of this magnetic field. So this is one realization. More recent ones are realizations of vortex lattices in rotating BECs. So there are beautiful experiments by Carnell, Catherine, and Dalibard group, which observe triangular repulsive vortex lattices in rotating BECs.
I'm sorry about the first line. You will assume that thickness is smaller compared to penetration?
I won't actually talk about this particular system.
Yeah.
I'll just talk about idealized system of 2D, 2-dimensional bosons in 2 dimensions.
Magnetic, my surface will not be important for you.
No, yeah, bosons are going to be neutral actually. Okay. Yeah, it's mostly going to be closer to BECs actually. So in this system, in rotating BECs, they really can only observe one phase, the repulsive vortex lattice, but it's very hard to reach low filling factors which are necessary for vortex liquids. From this point of view, the most promising system probably is the system that's studied by Ian Spillman group at NIST. So this is BECs in so-called synthetic magnetic fields. Basically what they do is they create beta phases for bosons using interaction of these bosons with light. Okay? And so they can reach filling factors, as far as I know, for the standard magnetic. Okay? So in principle, they should be able to reach fractional quantum Hall states or incompressible vortex liquid states soon. Okay, so what about the phase diagram? So the most important parameter here is the filling factor, okay, which I can define as the ratio of the number of bosons to the number of vortices. Okay, and so there are, as I said, there are two groups of phases basically. So at high filling factors, you have a repulsive vortex lattice. So this is a typical picture of a repulsive vortex lattice, which is observed in VCs, for example. This is actually a calculation, not an experimental picture, but the experimental pictures look similar. Okay? So then, as you reduce the filling factor, theoretically at least, as you reduce the filling factor, phase fluctuations become stronger and stronger. So you can think of the phase fluctuations as sort of motion of vortices, right? And so eventually, at low enough filling factors, and so these are filling factors of order 1, there will be a transition from an abricosive vortex lattice, which you can think of as vortex crystal, to a vortex liquid. Okay? So these vortex liquid states will typically occur at sort of commensurate filling factors, and in between there will be presumably re-entrant superfluid states. And so, so the useful way to think of these vortex liquids is that these are analogs of fractional quantum Hall states for bosons. These are analogs of fractional quantum Hall states that are observed for electrons in 2D electron gases for bosons. Okay?
So this would occur for a large number of vortices or a small number of bosons.
So this will occur for filling factors of order 1. So number of vortices of the same order roughly as the number of bosons. Of course, in this limit, you know, it's not even clear what the vortex means, right? So in this case, the filling factor is better thought of as just Landau level filling factor. So I'll talk about this later. Okay, so this is a picture from a sort of pioneering, theoretical work on this subject by Cooper, Wilkin, and Gunn from 2001. So what they did was just exact diagonalization study of this system of rotating BEC. Okay? And so what is plotted here is a gap from the ground state to the next excited state. Well, the way they calculate it actually is a gap to add the particle to the condensate as a function of the filling factor. Okay? And so you see that at relatively large filling factors, greater than about 6, the gap is 0, right? So this is consistent with the state being just a compressible abricosive vortex lattice, a superfluid, right? However, at filling factors less than about 6, the gaps open up at integer and half-integer filling factors. Okay? So this is consistent with the transition as a function of the filling factor into these incompressible vortex liquid states, or fractional quantum Hall states. Okay? So what are these incompressible vortex liquid states? So it's best to think about them in the limit of very low filling factors, less than 1, because then you can really make an analogy to fractional quantum Hall states of electrons. Okay? So let me discuss a couple of examples of such states. So I will assume henceforth that I can restrict myself to just the lowest Landau level. I will assume that the interaction between the bosons is always much weaker than the cyclotron gap, and so then I can just consider bosons interacting bosons in the lowest Landau level. Okay? So then I can think of the filling factor as simply as the usual lowest Landau level filling factor, right? The ratio of the number of particles to the number of single particle states in the lowest Landau level. Okay, so so in this regime, for filling factor less than 1 incompressible vortex liquid state is simply nu equals 1/2 Laplace liquid. Okay, so this can be shown to be the exact ground states for bosons with contact interactions. Okay, so this is an incompressible state. It has a gap to all excitations, and it has topological order. So it has a non-trivial degeneracy when the system is put on a torus, let's say.
What exactly physically is this fractional filling factor 1/2? So it means you have one boson per 2 vortices, right?
Well, it's better not to think in terms of vortices, because when
think in terms of angular momentum.
So it means no. So you should think in terms of filling of the lowest Landau level, right? So there is a certain number of states in the lowest Landau level, which is equal to the number of flux quanta through the sample. And so the number of you fill lowest Landau level with bosons, with interacting bosons, and so filling factor 1/2 is just 1 boson per every 2 states. But of course, you know, the vortices are not well defined in this.
But
why
we
you
want
call
the
it
momentum of
vortex
this
this way?
to be what in this function. So it's yeah, it will be 2n where it's the number of vortices, the number of bosons. So it's 2 units per particle.
Right, yeah.
Okay.
Yeah, that's right.
But then why call it a vortex liquid if it's not really a good way to talk about it?
Well, okay, it's a matter of terminology, right? Yeah, I don't have to. Maybe a better way to call it is a bosonic fractional quantum Hall state. Just that, you know, so the Abrikosov vortex lattice state is the vortex solid. As you reduce the filling factor, vortices will fluctuate more and more, and eventually they will sort of disappear into the liquid.
But the fluctuations here, are they big?
The fluctuations of
the positions of each atom.
sure, yeah. I mean, it's better to think of this in terms of fluctuations of the phase of the bosons, right? So in a superfluid state,
The reason I'm asking is because the same function here describes the distribution of random levels in levels of random matrices,
okay.
depending on the symmetry of the matrix. And there, actually, the levels are, the distribution is pretty rigid.
Well, I mean,
so that's the reason I'm asking.
This state is highly correlated, right?
Yes,
So certainly.
so they move,
So-
but only a little bit around the equilibrium position. So I would call it liquid then. It's
Well,
more like
okay,
quantum.
It's a liquid. Okay, so no. Crystal will break a symmetry, right? Crystal will break translational symmetry. This does not break any symmetry.
Well,
In this
if
sense,
it's
it's
one
liquid.
particle, you would.
Sorry.
If you pin one particle, you would.
Sure, but if you don't have any pinning potential, then this would be no. I mean, pinning.
One particle
No,
out of
crystal spontaneously breaks a symmetry, right? Spontaneously breaks translational symmetry without any pinning. If
Not sure.
Maybe you must clarify the model. Do you assume that rotation frequency is exactly equal to the critical, or
so this is just so let's say I'm talking about just interacting bosons in the lowest Landau level. Let's not really.
okay?
think
So
about
this corresponds
specific-
exactly if it's equal to rotation is equal to
Yeah, sure.
let's
Yeah,
say.
that's right. That's right. Yeah. So it's a liquid because it does not break any symmetries. It's a fissional state. That's basically by definition a liquid. Because a crystal would break symmetry of space, would break translational symmetry, and it has a finite correlation length, right? So in this, I would call this such a state liquid. I mean, again, it's a matter of terminology, I guess. You don't have to, but
Oh, but liquid is
Still liquid.
defined the thing.
okay. So another example is the fractional monopole state of filling factor 1, right? So in the case of electrons, the monopole state of filling factor 1 is trivial, right? You just fill all the states in the lowest Landau level. In the case of the bosons, this state is actually very non-trivial, so it's thought to be an example of a Moore-Reed state.
What is GS?
Sorry?
GS.
Ground state, sorry. Ground state is a Moore-Reed state. So this is the wave function. So it has very non-trivial properties. Again, it has non-trivial degeneracy on the torus. And it also has quasi-particles with non-abelian statistics and so on. So these are just a couple of examples of such
Can you
interactions.
remind of what the Fackian is?
Fackian, so for a skew-symmetric matrix, right, for a matrix whose transpose is the negative of the matrix, its determinant is a square of the Fackian. So Fackian
So
is
for two
basically square
particles,
of
it will be 1 over z1 minus z2 squared.
so for two particles, so basically the determinant of this matrix is square of the Fackian.
So in that case, it will be simply the modulus for two particles, the modulus of the
Well,
separation.
it has no, there is a sign, of course.
But it's
So not
Two
always
particles
positive.
wouldn't cancel the other factor then?
No, because it's not, no. So
Oh, okay. You see, the function is the square or the square root?
the square root of the determinant.
Square.
So
But
determinant
in that
is
case,
the
for two
square.
particles to be 1 over the modulus of z1 minus z2. And then the only thing which is left would be the phase, which will be, it will be a very singular wave function kind of.
No, that's okay. Basically, so the way that this wave function is written down, so you want to write down a wave function first that has the right filling factor, right? So without this factor, this wave function obviously has the right filling factor, right? Filling factor is 1, but then the problem is that this wave function is antisymmetric, right? So it cannot be a many-body wave function for bosons. So this function takes care of the sign under exchange. Okay, so this makes this wave function symmetric.
Basically, able to make z I and z j equal, kind of. So basically,
Right.
So what would be the wave function for two bosons?
Can you write it down? This is not going to be important for
No, I'm curious to see what it is.
No, I won't be able to do it right now. So that's not. We can talk about this after the talk. Okay, so let me finish with the introduction now and actually move on to my work. Okay. So what I will show you is that the problem of interacting bosons in the lowest Landau level can be mapped onto a problem of interacting bosons on a lattice in zero magnetic field. Okay? The lowest Landau level filling factor will translate under this mapping into lattice filling, right, which is the number of particles per site in this lattice. The abricosive vortex lattice phase will correspond to gapless compressible phase in this lattice boson problem, and vortex liquid phases will correspond to incompressible or mod insulator phases in the lattice model. Okay? And so in the rest of the talk, I will show you how this mapping works. So in principle, the fact that that a fractional quantum Hall liquid can be mapped onto a mod insulator should not be surprising, because even superficially, there are strong similarities between fractional quantum Hall liquids and mod insulators. So what is the similarity? Let me just, what is the superficial similarity? What is a fractional quantum Hall liquid? We take lowest Landau level. Okay? Lowest Landau level has a macroscopic number of degenerate single particle states, which is equal to the number of flux quanta to the sample. And then we fill these degenerate single particle states with repulsively interacting particles at certain filling factor, right? And at certain rational filling factors, we get incompressible states. Okay, states with a gap to charge excitations. Okay. Now, what is a mod insulator? Mod insulator is actually a very similar thing, right? So let's think about mod insulator in 2 dimensions. So we have some crystal lattice, 2-dimensional crystal lattice, let's say square lattice, right? To each side of the lattice, we have a Vannier orbital associated to it, right? And so we have degenerate Vannier orbitals, and we fill these Vannier orbitals with particles, with repulsively interacting particles, right? And at certain filling factors, depending on the details of the interaction between the particles, we get again incompressible states, which are mod insulators.
How do you define incompressible?
Incompressible, there is a gap to charge excitations. There is a gap to all excitations, basically.
So when you say the gap is incompressible?
It's the same, it's equivalent.
Incompressible, it means you're going to modify the volume of the density.
It assumes that lattice is uncompressible on definition.
Right.
And then the electrons will be incompressible.
Right. Yeah. It's equivalent.
The body will be compressible, of course.
So for the square lattice here, you have the fillings at the rational ratios. But for the say the fractional quantum Hall effect, is, I thought steps like 1/3 were more dominant than say steps at 1/2.
Well, no, this is just, again, this is just, you should not take this, this is just an example. Right? Actually, for bosons, the dominant fractional quantum Hall state is at filling factor 1/2.
Okay,
For electrons,
so-
it's 1/3. But this is just sort of hand waving picture so far. This is not theory yet. Okay, so this is an example of a simple Mott insulator for particles at filling factor 1/2 on a square lattice. So if you have particles at filling factor 1/2, right, if these particles have strong enough near neighbor repulsive interactions, they will crystallize into this kind of Mott insulator state. Right? So here you can see an important difference between fractional quantum Hall liquids and Mott insulators. So fractional quantum Hall liquids fractional quantum Hall liquid is a liquid, right? So it's featureless, doesn't break any symmetries. Mott insulators at such fractional filling, as you can see from this picture, will generally break lattice symmetry. Okay?
What that means typically?
Typically, it means that for if you write down a reasonable Hamiltonian for bosons on a lattice, right, let's say with interactions that fall off this distance, typically any kind of Mott insulating state that you will get will break. You'll break symmetry. So you need an unusual form of the Hamiltonian to get a Mott insulator that doesn't break a
But
symmetry.
in this case, it will be not a Mott insulator.
No, it will still be a Mott insulator.
No?
No, it will still be a Mott insulator. The definition of Mott insulator is that this is an incompressible state, right? It doesn't have to break a symmetry.
No, it's any dielectric is incompressible from this point of view.
Sure.
Yes, but it is, it will have a gap because of symmetry, not only because of interaction. Yes.
Sorry, I'm not sure what you mean.
Okay. Let's take band insulator. Yes.
Right.
It does not depend on interaction at all. You have gap due to the symmetry because you have two electrons per side. Yes. And I believe that after this phenomenon, you will have doubling of the period, and you will have gap number of sides.
That's right. Yeah.
Okay.
Yeah.
Okay. If it's okay. If it's okay.
Yeah.
If you're off commensurability, is it really a liquid with broken symmetry on this lattice, or is it just like you have a hole hopping around and there's still symmetry and such from the lattice?
Well, if I'm off, if I dope, let's say, if I dope this crystal, well, so it depends, right? Let's say for hardcore bosons, if you dope this kind of crystal, it will actually phase separate.
But is it important for you?
No, it's not important. This is just
Exactly.
This is certainly not important.
Okay.
Okay, so what this shows basically is a fractional quantum Hall. The mapping is not between fractional quantum Hall liquid and any insulator. It's between fractional quantum Hall liquid and featureless Mott insulator. Okay, this is one of the reasons I think that this is interesting, because for certain people this is for a lot of people this is sort of it's like a search for a holy grail, trying to find instances of featureless Mott insulators that don't break any symmetries. So this also goes by the name of spin liquids, I guess. And so even though a lot of progress has been made on this, even experimental one and theoretical one certainly, sort of the general features that a Hamiltonian of, let's say, interacting bosons must have in order to get a featureless Mott insulator state, these are not known. Okay? And so this mapping, I believe, can be useful for this. Okay, let me just mention briefly some related work. Probably the earliest work that's similar in spirit to what I will talk about is this work of famous work of Kalmer and Laughlin, who proposed that ground state of triangular antiferromagnet, Heisenberg antiferromagnet on triangular lattice is actually nu + 1/2 Laughlin state. But this turned out not to be true, of course. We know that triangle analysis is ferromagnet orders. Right? It's not a featureless state. But nonetheless, this is an important work. There was a more recent work on fractional quantum Hall states on a thin torus. So what these people have shown is that if you put your system on a torus and then reduce circumference in one of the directions of the torus, the fractional quantum Hall liquid actually becomes a crystal. Okay? So these are all similar in spirit to what I will talk about, but so it's, I don't really have time to discuss them in detail. Okay, so let me move on. So why is it not trivial to make, so even though there is certainly, as a there is certainly a similarity between fractional quantum Hall liquids and not insulators superficially, why is it not trivial to make this connection precise? Okay? And it's not trivial because of problems with notation, basically. Okay? The problem is that the standard choices for lowest Landau level orbital eigenstates, for example, eigenstates in a Landau gauge, are not localized. Right? So, for example, eigenstates in the Landau gauge are localized in one direction, but are plane waves in the other direction. Right? So what this does is that this makes energy penalty for W occupying such an orbital vanish in thermodynamic limit. Right? Then it becomes very hard to make an analogy to a Mott insulator because we typically think of Mott physics as being due to excluding double occupation of some orbitals or groups of orbitals. So what we need to make this connection explicit is to choose lowest Landau level basis, which consists of wave functions localized in all directions in the 2D plane. So kind of similar to linear functions in insulators. Okay? So there immediately seems to be a problem with it. So it's known from the work of Paulus and other people that exponentially localized linear functions are actually incompatible with this topological property that every Landau level has, a non-zero Chern number. Okay? So then this seems impossible, but actually it turns out to be possible to construct quasi-localized linear functions, which are normalizable, right? So the integral of a square modulus of this function over the 2D plane is finite, but they have this power law tail. Okay? So this is okay for my purposes because even with this 1 over r squared tail, the energy penalty for W occupying such an orbital is finite. Okay? So I don't actually need exponentially localized orbitals. And so it was shown in this very nice work by
Is it possible to normalize function with such a tail?
No, it's possible. In 2 dimensions it's possible. Right? It's 1 over r to the 4th integral over 2D plane.
Oh,
Yeah, it's possible. So
what's about the positions of this linear function?
right, yeah, I'll talk about this. Yeah. And so it was shown how to construct such a basis in this beautiful paper by Rajba and co-workers. And so let me show you how it's done. Okay? So I'll call this basis of such quasi-localized, quasi-linear functions magnetic linear basis. Okay? So this is the way that this basis is constructed. So we choose, let's say, symmetric gauge. Okay? And I start from a particular symmetric gauge wave function which corresponds to zero angular momentum. Right? So this is this wave function. It looks like an atomic wave function which is centered at the origin. Right? Just a Gaussian orbital centered at the origin. So then what I do is I translate this wave function to sites using magnetic translation operators, which commute with the Hamiltonian, to sites of, in principle, any 2D Bravais lattice. The only restriction is that there has to be exactly one flux quantum per unit cell of this lattice. Okay? So what this does, of course, is that, first of all, it preserves the correct counting of states. Right? So there is still exactly one state per one flux quantum. Right? The second thing it does is the following. So you know that generally translations in different directions in magnetic field do not commute. right? But in fact, translations by basis vectors of such a lattice is exactly 1 flux quantum per unit cell do commute. Okay? So then it turns out that you can, if you define your states on sides of such lattice, you can actually introduce block momentum and so on. Okay? And then find Monier functions. Okay. Okay. So this is what the wave functions, the translated orbital looks like, right? So again, it looks very similar to atomic orbital centered at sides of this lattice, except for this phase factor. Okay.
And if I go around each triangle, it will be 2 pi.
So yeah, if you go around, it's not triangle, right? So it's per unit cell. So if you go around each 4-side plaquette, it's going to be 2 pi. The phase is going to be 2 pi. Right? So this set of wave functions looks like right. And so so as I said, in principle, this lattice can be any 2D Bravais lattice. But I'll show you, as I'll show you later, the best choice is in fact triangular lattice. Okay. So from now on, I will assume that this lattice is triangular lattice. So this set of wave functions looks like. You will see. You will see what it means just in the next slide. So this set of wave functions looks like just set of atomic orbitals, right, in an insulator. But there is a very important difference. So this set of wave functions satisfies this amazing identity. So at any point in space, sum over sides, Cm of r multiplied by this factor, is always equal to 0. Okay? So in fact, this set of functions is overcomplete by exactly one state. Okay? So this identity follows from the theory of theta functions. So basically, these sums can be expressed through theta functions, and this is one of a million theta function identities. And so this was first shown by Perelov in the 70s.
So what's the reason for this overcompleteness?
The reason, well, so formally, again, this just follows from, this is a theta function identity, formally. From here, it actually follows that you cannot construct exponentially localized Monier functions. You will see why. So, yeah, I don't know what is the...
There is a result like this in coherent states. You can
Right,
choose
yeah.
coherent states, one per phase-based cell. In that system, it's exactly overcomplete in the same sense.
Right,
There is
yeah.
one single extra
Yeah,
wave function.
yeah, it's the
there.
same. Yeah, it's the same.
So it's identical to that result.
Yeah. So this, as I will show in the next slide, is actually the origin of this non-trivial topological property of block states in the Lobst-Landau level that have non-trivial Chernow.
Question.
Yeah.
But this overcompleteness identity. If you think about a finite system, say on the torus, and you think at the total number of basis functions you should have, are you missing one?
No, you have one extra.
No, because you're taking a wave function now and translating it to each unit cell.
Right.
You have one per unit cell, but then you have the overcompleteness theorem, so you're missing one. You actually have the exact same thing in flat band.
Right. So this identity strictly applies to an infinite.
Of course.
An infinite system.
Yes.
So what this missing factor means for flat band?
So for flat bands, what this means is that you have a state, you have outstanding states apart from this basis, which go around the non-contractible loops of the torus.
I think this
Okay,
is
so
like
these are like
Fourier transform. You see, the last state, it's always...
So is it some kind of
You
surface
reproduce
state,
it
so
because
H
it's
state?
three
yeah.
boundary
I mean,
conditions.
yes. So
So I
certainly
think it's the same thing.
that probably is a relation to H states, right?
Uh-huh.
Because so due to the fact that Landau level is characterized by a short number. If you actually have system with edges, it follows from here that you have edge states. So probably there is a relation, but I don't know what this is. I mean, this will actually not play any role in what I will talk about.
Can you show that it is 1 over r squared tail here? Where is the origin?
That will come in the next slide. Yeah. Okay. So given this over-complete set of atomic-like wave functions, I can follow the standard procedure from Ashcraft and Norman to construct first magnetic block states out of linear combinations of these atomic orbitals. Right? So the momentum k here belongs to the brilliant zone of the triangular lattice. Right? And so, given block states, I can then do inverse Fourier transform to construct Wannier states. Okay? And so these Wannier states form a complete orthonormal set of states, basically by construction. Okay? So the way that this identity enters in here is the following. So the block state, if you want to normalize it to 1, right, it must have this normalization factor, which depends on momentum. Right? This normalization factor follows from this identity almost immediately that this normalization factor vanishes at one point in the brilliant zone, at pi pi. Okay? So there is a singularity of the block function at this point in the brilliant zone. It can be shown that this block function is still well defined if you carefully calculate the limit of k going to this point. But there is nevertheless a singularity, right? And so when you do the inverse Fourier transform to calculate the Wannier state, it is this singularity in the momentum space that leads to power law. Okay.
So then the sum is 0 because of the previous relation and the square.
That's right, and then the limit.
0 and the big cancel each other.
The singularities cancel, so the limit. So this was all shown in this paper by Rajba. Okay, so I will just use this basis. Okay. Okay, so given this complete orthonormal set of states, which look like Wannier states but with power law tail, I can rewrite a Hamiltonian, any Hamiltonian for interaction bosons in the lowest Landau level using this basis, right? And so this is what the Hamiltonian will generally look like, right? So there is no kinetic energy because I'm restricted to the lowest Landau level, and so this is the matrix element of any, in principle, any interaction. I will take this interaction to be quantum, let's say. Okay? So these matrix elements can be easily calculated in general, only numerically, but it's still very easy, right? So what you can say about them in general is that they are all finite in thermodynamic limit, and they fall off this distance as 1 over r to the 6. Okay?
This is for short range interaction or?
Yeah, for short range interactions, that's right. For if I take V to be contact interaction, this matrix element fall off this distance between the sides as 1 over r to the 6. Okay? So this is short range. I think you will agree with me that this means that these matrix elements are short range, and so I can restrict I can cut them off at maybe nearest neighbors or next nearest neighbors. Cut them off at few nearest neighbor distances. Okay? However, even if I do cut off these matrix elements at short distances, there are still a lot of non-zero matrix elements. Okay? Because the only symmetry these matrix elements have is the symmetry of the triangular lattice. Okay? So there are a lot of different matrix elements. They can different terms in the Hamiltonian compete with each other, and so in this form, this Hamiltonian is completely useless. It's very complicated. The reason that this is complicated is, this is the usual problem in condensed matter physics. So this Hamiltonian is the full microscopic Hamiltonian, right? And so, as such, it contains a lot of unnecessary information, right? What I want to do now is derive a low energy Hamiltonian. So typically, simplicity appears at low energies, right?
I missed why cannot restrict to nearest neighbor?
Why I can? I can.
Oh, you can.
I can, yeah, because
It's
it's
still
short range.
complicated.
It's still complicated because you'll have a lot of different matrix elements. In general, they're complex. If you just try to enumerate all possible such matrix elements where M1, M2, M3, and M4 are nearest neighbors, there is lots of
You get things like correlated hopping.
right. Correlated hopping, I mean, many different types of matrix.
Isn't the Hamiltonian simple in the original coordinate representation because it's on-site repulsion, so it's so simple it cannot be any simpler. So you now introduce by using this basis set, you see a certain range, and in a way you complicated the matrix.
No, so the point of this is to transform the original Hamiltonian of bosons in continuum moving in a magnetic field into a Hamiltonian of bosons without magnetic field. And so the contribution of the magnetic field will just be so the information about the magnetic field will be in the wave functions, but not in the matrix elements. In the matrix elements of the low energy Hamiltonian.
So that amounts to diagonalizing the one-body part of the Hamiltonian and then taking care of the two-body part. Is what you're saying?
Well, yeah. You will see how this works. And so it actually turns out that there is a very nice hidden symmetry in this Hamiltonian that appears at low energies. Okay? In the sense that I will describe. Okay? Okay, so to start, let me now look at the physical meaning of these magnetic block states. Okay? So using, again, this amazing Krylov identity, it's very easy to show that the zeros of the block states themselves form a triangular lattice. So if I choose this lattice of magnetic Vannier states to be triangular, the zeros of the block states themselves form a triangular lattice with exactly one flux quantum per unit cell. Okay? And so the zeros are allocated at these points. So you see that the momentum of the block state just labels the center of mass position of this lattice of zeros relative to the triangular lattice of the magnetic Vannier states. So since wave functions in the lowest Landau level are fully specified by their zeros up to phase factors, right, we can immediately identify block states with abrikosov vortex lattices in the lowest Landau level. Right? So this is because any wave function in the lowest Landau level is fully specified by the zeros up to phase factors. So then we know that the ground state of this Hamiltonian at large lowest Landau level filling factor is the abrikosov vortex lattice. Right? So in the magnetic block state language then, the ground states of interaction bosons in the lowest Landau level at large filling factors correspond to condensation of the bosons into block states with particular block momentum. Okay? So let's see now what this means when we what this means in the magnetic Vannier basis. Okay? So this is the connection between the creation operator for the boson in the Vannier state to the creation operator for the boson in the block state. So if I condense bosons into a state with a single block momentum, right? What this means in the Vannier basis is uniform phase winding for the bosons, right? Where the phase winding rate is K. Is this momentum into which I condense the bosons, right? So the abrikosov vortex lattice in the language of the magnetic Vannier states correspond to all possible states with uniform phase windings along basis directions of the triangular lattice.
So does it mean that there is a missing vortex for a regular abrikosov lattice?
Sorry?
Like if I use Krylov identity, does it mean that if I consider a regular abrikosov lattice, there is a missing vortex somewhere?
No. So this
No, I'm just using your analogy.
This basis, the basis of magnetic Vannier states, is not overcomplete. It's complete and orthonormal.
Okay, right.
Okay. So the abrikosov vortex lattice states correspond to states with uniform phase winding. So uniform density and uniform phase winding along the basis states of the triangular, along the basis directions of the triangular lattice. Okay, so this has this nature of the recursive vortex lattice states in the linear representation has very important consequences. So first consequence is, so let me take a recursive vortex lattice state, a particular vortex lattice state, and look at small phase fluctuations, small fluctuations around the state. Okay. So since all states with uniform phase gradients are degenerate, right, the action for phase fluctuations will lack the usual, gradient of theta squared term that we have in superfluids. Since all uniform gradients have the same energy, right? So the lowest order gradient term that's allowed is grad squared theta squared. Okay. So this means, in particular, that the dispersion of phase fluctuations is going to be quadratic. In the recursive vortex lattice state is going to be quadratic instead of linear. Okay? This is actually a well-known result that has been obtained before by a number of authors by different means. So I believe that this kind of magnetic linear language provides with the simplest derivation of this result. Is this clear? Yeah.
Can I ask a slightly different question? Is it correct to say that once you define the field factor, you define this basis set, you define the triangular lattice, you define both sizes, and you change that, then you'll change the
So
the size.
you must have, so you must have the area of the unit cell must be 2 pi times magnetic flux squared.
You cannot understand the last statement, because if we have such excitations, they will be distributed at final temperature with the Bose distribution, and it cannot be moved with respect to...
That's right. So what you are saying is that it cannot be superfluid, this kind of quadratic dispersion. So this is not quite true. So what happens is that, so if you have a quadratic dispersion, long-range phase order is impossible. Right? So the phase correlations will fall off as a power law. However, if you look at fluctuations of the positions of the vortices, they are still finite. So the vortex lattice is still there.
The question of long-range order is a different question. Superfluidity is the property not of density matrix but of the real correlator. So it's impossible to move elementary excitations with respect to superfluidity.
Well, so this is like, I guess, okay, so the
If
phase...
you will say me that the density matrix decay algebraically, it makes no difference. It's not important.
I mean,
important real excitations.
I mean, I would say that it's superfluid because the vortices are localized. Vortices are not moving. I agree that it's a non-trivial question. And,
so if the vortex is not, it's not superfluid.
Yeah.
Okay.
Well,
Actually,
because there is no, the phase
superfluid
difference.
in presence of vortices. It is not superfluid because there is a mutual friction. Probably this is related to this.
Sure, yeah, the vortices, the vortices have to be pinnates. So, yeah.
Okay, but it's better to understand.
Okay, but so for me it doesn't really matter whether this is superfluid or not. Okay, so.
Just curiosity, so if you start from square lenses, will you get the same picture, or
It's just that, so yeah,
linear states will form,
right.
Square
Right.
consequences?
Yeah, so you will get square recursive lattice, it's known that this is not the lowest energy state. But
Yes, but in principle the analysis
sure,
will
in
go
principle the
through,
analysis
so
will
you
be the
derive
same,
this.
yeah.
So, but the vortices don't move because of the fact that you put them on a lattice?
The vortices don't move because the quantum fluctuations are not strong enough to disorder the lattice.
But this is liquid, so they have no position at all.
No, this is no. I'm talking about the recursive vortex lattice state. So far, I'm talking about the recursive vortex lattice state. Okay, so
Okay, but the state is obviously non-superfluid. Because there is mutual friction, so there is no contradiction.
Well,
This is right rotating superfluid. It's no superfluid in the sense of the word.
well, you're saying that the vortex is cut and pinned by something.
Okay.
Yeah.
Yes.
Okay. Yeah. Probably.
I wouldn't. There is no contradiction in the case.
Sure, but so if the vortices were in a liquid state to begin with, then even pinning would not help you, right? So here the vortices are on the lattice, and any pinning by boundaries or
It's
yeah,
a
pin single
one
vortex.
vortex.
Sure, yeah.
Two stop.
Then, yeah, that's right. So in this sense, it's but this okay. So for my purposes, really the most important thing is that the absence of this grad theta squared term in the phase action can actually be shown to be a consequence of the conservation law that emerges. Okay, and so this is how you see this. So let me again look at this at my Hamiltonian for interaction bosons in the lowest Landau level in the block basis, in the magnetic block basis, not in the magnetic linear basis. So since all block functions with different momenta simply correspond to different abricosal vortex lattices, simply translated in the 2D plane, right? All block functions must be related to each other by magnetic translations. Okay, and so this is the exact relation where so this is a phase factor. This is just I don't know for a phase factor. And this is an additional momentum-dependent phase factor. Okay, so this is an exact relation between block states at zero momentum and some finite momentum k. Okay, so it follows from this relation that this interaction matrix element is actually independent of this common momentum k, as long as the excitation momenta q and q prime are small. Okay? So it immediately follows from this relation between the block states at different momenta. Okay? So then, if I now Fourier transform this back into the Wannier basis, the fact that this matrix element is independent of the momentum k leads to this form for the matrix element in the Wannier basis. So there is some function which is not important. So the important thing here is this Kronecker delta symbol. This Kronecker delta symbol expresses conservation of the center of mass of the bosons in any collision process. Okay? So this Kronecker delta symbol simply arises from the independence of this matrix element on this momentum k. Okay? So then what we see is that the Wannier basis Hamiltonian in the abricosal vortex lattice phase has emergent center of mass conservation if I consider sort of low energy, long wavelength fluctuations of the abricosal vortex lattice state.
Is it related to the angular momentum conservation? Because that's what you get something similar.
No. So, I mean, generally, these matrix elements do not conserve the center of mass. So this only happens sort of at low energies when you consider small fluctuations about the abricosal vortex lattice. Yeah.
You essentially have the same sort of low energy symmetry in the quantum Hall state in this work by Seidel and Donai.
Sure.
But is
this
it exact
only
over
in one direction, right? So if you write this Hamiltonian in the Landau gauge orbital basis, this looks like Hamiltonian of bosons on a 1D chain.
Yeah.
And along this chain, there is this center of mass conservation is exact.
Okay.
But here, this is on 2D, right? This is on the 2D lattice.
Why different processes are not for low energy, potential short range?
So it's simply that I'm just assuming that so I start from an abricosal vortex lattice state, right? So in this case, I can just set Q's to 0. Okay? And then, so I'm considering long wavelengths fluctuations of the abricosal vortex lattice. So Q and Q prime are small compared to the the size of the brilliant zone.
So you can show that low energy excitations in these long wavelengths. Because in principle, if you have such a degeneracy, there's no
So, yeah,
penalty of
well,
having
it's very easy to see that the Hamiltonian you get if you assume that this is true exactly gives you a precursive vortex lattice and the right dispersion of small fluctuations.
So in a usual abrikosa lattice, you have compression and shear. Compression, okay, is large, but shear is not. So, and usually it gives you k squared. So how do you avoid that here?
Sorry, I didn't quite.
Like you have, okay, if you look at the positions of vortices, the compression modes and the shear modes when you don't change the density. So the shear usually gives you k squared too. So how can you avoid that?
No, this contains everything, right? This is just I'm only assuming. So I'm starting from the abrikosa vortex lattice state, which in this language is simply state with any uniform phase gradient, right? And then I consider small phase fluctuations about this state.
Phase means that you actually move position of vortices, right?
Well,
or anything.
In this language, this abrikosa vortex lattice state looks different. There are no vortices, right? Because the information about the vortices is in the wave functions, right? So here, because the vortex lattice state simply looks like a state with any uniform phase length. There are no vortices in this.
I understand, but your label, I mean, your function has zeros, and you said that you can trace the position of every zero.
Right.
And if you move the zeros, that gives you.
I mean, I cannot trace position of every zero. So every block state corresponds to a particular fully ordered abrikosa vortex lattice. Momentum simply labels the center of mass position of this lattice. Okay, so if you believe that this is correct, that this Wannier basis Hamiltonian has this emergent center of mass conservation symmetry, then I can just write down effective low energy Hamiltonian in the abrikosa vortex lattice state. Okay, so it has this very simple form, right? So what I've written here is all shortest range terms on the triangular lattice that conserve the center of mass. Okay, so these are so these terms are simply repulsion terms, right? So on-site repulsion, maybe nearest neighbor and next nearest neighbor repulsion, they obviously conserve the center of mass. So the only kinetic term that I have is this ring exchange term. Okay, so what ring exchange term does is that so you take one plaquette, one rhombic plaquette of the triangular lattice, and you hop, let's say, two bosons on the opposite corners here to different opposite corners. Right? So the significance of this ring exchange term is simply that this is the shortest range boson pair hopping term on the triangular lattice, which conserves the center of mass. Right? So obviously the center of mass is conserved. Right? The center of mass is at the center of the plaquette here, and it's in the same point here. Okay? So my claim is that this is the low energy Hamiltonian for in the abrikosa vortex lattice phase. Okay? So let me do a simple sanity check, right? So let's take this Hamiltonian. Let's send the filling factor to infinity, right? So when I send the filling factor to infinity, the boson creation operators can be just replaced by C numbers, right? The density is made uniform by these by the repulsion terms, and so then this Hamiltonian simply maps into this classical Hamiltonian, which depends only on the phases of the bosons, right? And it's very easy to show that the ground state of this Hamiltonian indeed consists of all states with uniform phase gradients. And as I've shown you already, these precisely correspond to abrikosa vortex lattices. So indeed, the classical ground state of this Hamiltonian at large filling factors is the abrikosa vortex lattice. And so if you calculate fluctuations, small fluctuations, you will get the quadratic dispersion. So this Hamiltonian describes correctly both the ground state and the excitation spectrum, and the low energy excitation spectrum. Okay? Okay, so now this was pretty much exact. Okay? Now comes the conjecture. So my conjecture is that the low energy Hamiltonian is the same at all filling factors. Okay? What I've shown you is that this Hamiltonian, this short range, this swing exchange and repulsion is the correct low energy Hamiltonian at high filling factors. My conjecture will be that this is the low energy Hamiltonian is the same at all filling factors. This is a conjecture. You know, it has to be shown to be correct or not correct by an explicit numerical calculation. But I'll make this conjecture. I think this conjecture is reasonable. This should certainly be okay. This can be justified almost rigorously for vortex liquids with, in which the correlation length is low. The correlation length is significantly longer than the magnetic length, right, which is basically the lattice constant of this lattice. And so, well, the only justification I can show you for this is, so again, if I look at this picture from the Cooper, Wilkin, and Gunn paper, you see that the gap, so when you go below the critical filling factor, the gap opens up smoothly. So, so at least for filling factors close to the critical filling factor, the gap is small. And so this will translate into long correlation lengths.
One question, so why is it not clear that the slow filling limit reproduces the slow energy Hamiltonian? Is it about the fact that the wave functions probably do not decay as fast for low fillings?
Well, I mean, obviously I've justified this only for because of vortex lattice state, right? My argument was specifically starting from because of vortex lattice, and I was considering small fluctuations.
So you're always in the limit of infinite filling. If it's exact.
Yeah. In the limit of large filling. So this is not, strictly speaking, not justified in the limit of low filling factors.
So even for intermediate filling, say order one or larger.
Well, as long so this is certainly justified as long as you are in a recursive vortex lattice state. So as long as you are in this phase, as long as you are above the critical filling factor, this is fine. And just by continuity, it's the same phase. So it will be justified below the critical filling factor, I would say, if the transition is continuous or at least weakly first order. So the gap does not jump immediately to a large value.
So is the solution for a model with the exchange?
No. No, it's not novel. It's just Okay, so let me just complete down the time. Let me quickly wrap it up. So let me rewrite this Hamiltonian in a more suggestive way, right? So I can replace boson annihilation operators by the square root of the filling factor times the I phase, right? And then introduce phase and the conjugate particle number, right? And so then this Hamiltonian will take this form, right? Where K now is proportional to the filling factor squared, right? And so, again, so I can look at the phase diagram of this as a function of the ratio of K over the repulsive interaction terms, right? So obviously at large K, which corresponds to large filling factors, the phase will be ordered, right? So this corresponds to the repulsive vortex lattice. As I reduce the filling factor K, this term becomes smaller, right? So quantum fluctuations of the phase increase, right? And so eventually the phase order will disappear, right? And so that will correspond to transition into vortex liquid states. Okay? So it seems reasonable that the same Hamiltonian should describe both the vortex lattice phase and the vortex liquid phases. Okay? Okay, so let me not, since I'm out of time, let me just conclude at this point, basically. So what I've shown is that the interaction bosons in the lowest Landau level map onto a time reversal invariant model of bosons, of interaction bosons on triangular lattice with ring exchange and repulsive interactions. Okay? So what I expect then is that at the filling factors at which the bosons in the lowest Landau level exhibit fractional quantum Hall effect, the ground state of this equivalent of boson model on triangular lattice will be a featureless mode insulator with topological order. Okay? And so the nice thing about this model is that this model actually does not have this infamous Monte Carlo sign problem. Okay? So all my assertions can be checked by quantum Monte Carlo simulations on large system sizes. Okay? Thank you. Yeah.
So if this is true, right, and they do confirm it on Monte Carlo, what do you, I mean, is there other things you hope to learn, or what is the...
Well, okay, so one thing you learn is that, okay, so the ground state of this Hamiltonian is a featureless mode insulator, right? It's certain filling factors. So this is a very relatively simple. I mean, so Hamiltonians which do exhibit such states have been written down, but they're usually very involved and very complicated and very artificial looking. Okay, so this Hamiltonian looks relatively simple. Okay, so it's just interacting bosons only with an unusual kinetic energy charge. You don't have usual kinetic energy, you don't have hopping, and they have this center of mass conserving hopping. Okay, so this may sort of show, you know, what this shows basically. So if this is correct, this shows what we need to at least one class of Hamiltonians in which such mode insulating states without any broken symmetry can be obtained. This shows what you need to get such states. Another thing, of course, is that, again, so this is much easier to simulate than directly bosons in magnetic field, right? For that problem, you can only do exact diagonalization at small system sizes. With such lattice model, you can do Monte Carlo.
One question: is it possible within this model to tune even this mod transition in some sense? Or
Tune
it's
and
just
coordinates.
I mean, can you access the mod transition, not only the mod insulator, but the mod transition?
Yeah, of course.
And which part of this Hamilton is responsible? Is just a U?
Right. Well, no. So it's a ratio of no. So both you can in principle get different kind of mod states, right? So for example, if let's say I'm at an integer filling factor.
I should maybe modify the question. Can you tune it such that the mapping is still valid onto this other model?
So okay, so the mapping onto fractional quantum Hall problem, you mean? So of course, this Hamiltonian has more phases, right? So the mapping to fractional quantum Hall only exists for specific in a particular range of parameters for specific values of these parameters.
So maybe the transition point is not accessible in the mapped model for the fractional quantum Hall.
No, I would say it should be accessible, but we need to tune U and V. We need to tune the relative strengths of U and V to access it. So obviously, you know, if U, let's say we are at integer filling and U is much larger than V, right? Then you will get a trivial insulator where you have one boson per site, or integer number of bosons per site. That's not, this is not a fractional quantum Hall state.